Okay, language for specifying lexical analysis. Okay, and in this, while discussing this thing, okay, we will look at how to translate transition diagram. Okay, so I'll use this X symbol for transition diagram, okay, to code, because ultimately we have to write a piece of code. Okay, so what we have till now, we have only transition diagram. So we have transition diagram. Okay, so we have transition diagram, and we need to translate those transition diagram into a code, and that kind of a code will be your lexical analyzer in that case. Okay, so input is this and output is this. Okay, this is your output. So in short, you can say lexical analyzer takes this input, which is a transition diagram, and it generates tokens. Okay, and this lexical analyzer is what your code is. Okay, so from transition diagram that you have, you need to translate those transition diagrams into code. I hope the purpose of this session is clear. What do we need to do? We need to see how to translate a transition diagram into a code, and that kind of a code will be a language. Okay, will be a language, okay, that we can use to specify lexical analysis. Is this clear? What we want to do? We want to convert transition diagram to code. Okay, so give me a feedback if it is okay. Yeah, tell me. Are you people there? Muskan, Neeraj, Nishant, Anmol?
Yeah, yes, sir. Yes, sir.
I'm asking you people, please respond. Is this clear? What is we are going to discuss today?
Yes, sir.
Okay.
I actually responded, but I think the mic,
Okay, you were muted.
there was some
Okay.
connection. Yeah.
Okay, okay. So I'm stopping a share one more time so that I can start a share a new thing. Okay. And do let me know whether this is clear to you or not. A language for specifying lexical analyzers.
Yes, sir.
Okay. So we are going to discuss this thing. Okay, a language for specifying lexical analyzers. And there are many tools which have been built for constructing lexical analyzers, as it is evident from the first statement. So for constructing a lexical analyzer, there are many tools which have been built. Okay, and these tools, okay, vary from simple purpose notations. This is simple purpose notation, okay, which are based on regular expressions. Okay, simple purpose notations which are based on regular expressions. Okay, so from these notations, there are many tools which have been originated. Okay, so this kind of dark green thing, okay, is a collection of special purpose notations, and these are based on regular expressions, and we have seen what regular expressions are in the last sessions. Okay, and we have already seen the use of regular expressions for specifying token patterns. We have also seen that, right? So how to make use of regular expressions to specify patterns for the tokens. And before we consider algorithms for compiling regular expressions, okay, into pattern matching programs, okay, we give an example of a tool. So we'll be looking at one particular tool that might use such an algorithm. Okay, see, there are many tools, and those many tools are based on SPN. Okay, what is SPN? Special purpose notations which are based on regular expression. This is how you can say there is a regular expression, and on the top of regular expression there are special purpose notations, and those special purpose notations, okay, those special purpose notations are responsible for generating many tools. Okay, and those tools are there for generating lexical analyzer. Okay, now we in this lecture we are going to consider one particular tool. Okay, we are going to look for one particular tool. Let's say that tool is this one. Okay, and that tool is Lex. Okay, we describe the particular tool called Lex. It doesn't mean that the Lex is only tool. There are many other tools. There are several tools. Okay, that has been widely used to specify lexical analyzers for a variety of languages. Okay, it could be C, C++, Python, Java, Basic, Fortran. Okay, variety of languages. You can use Lex to specify lexical analyzer. Okay, and we refer to the tool as Lex compiler. Okay, we say that the tool, though it is called Lex, but we refer it to as Lex compiler. And to its input specification, we say that Lex compiler is a tool. Okay, Lex compiler is a tool, and its input is based on regular expression. Okay, and it says that, and its input specification as Lex language. We say that its input is Lex language. Like C compiler has an input called C program. Similarly, Lex compiler has an input. Let's say this is an input. Okay, Lex language. Okay, so its input specification is a Lex language, and discussion of an existing tool will allow us. So if we discuss the existing tool, and this is an existing tool, which is a Lex compiler, it will allow us to further see whether we can create similar kind of tool in future or not. Okay, so you just need to take this point into consideration, that if you are going to create this kind of a tool, let's say Lex compiler, let's say you in future you decide that, okay, I'm not going to use Lex, but I'm going to create my own Lex compiler, or some kind of a compiler that is used to design a lexical analyzer. You have to take this thing into consideration, that your tool should be based on SPN, special purpose notation, which are based on regular expression. Okay, so Lex is one tool. You might decide that you are not, let's say when you analyze a particular Lex compiler, you will figure it out that there are some shortcomings in that compiler which you can improve. Okay, so if we are going to discuss an existing tool, we are discussing existing tool, and it will allow us to show how specification of patterns using regular expressions can be combined, okay, with actions. For example, making entries into the symbol table. Okay, like when I discussed this Lex compiler to you initially, when I talked about Lex language, I mentioned that Lex language program written in a Lex language is composed of three sections. The first is a definition of manifest constants. Then you have the transition rules. Okay, and these transition rules, which is the second component, okay, it describes how to translate the regular expressions into actions, how we can club regular expression into action. Like this was this second component was saying that if you get a tab or something, let's say, or a new line, okay, or a blank space. Okay, I mean to say, if you encounter white space, then do nothing. Okay, do nothing operation. And if you encounter some relational operator, then return relop. Okay, if you encounter something which is qualified to be an identifier, then you have to install that identifier into a symbol table. Install id, right? Install num if you find a pattern for num. Okay, so this second component of that Lex program was talking about that association of the regular expressions to actions. So action is written as a second column. Okay, and regular expression was written as a first column to the second part of a Lex program. And the third part of the Lex was about the auxiliary procedure. Auxiliary procedure, like in order to do that installation of identifier into a symbol table, or installation of a number into a symbol table, you need to call subroutines, and those subroutines are auxiliary procedures, which are written in the third portion of a Lex program. Okay, for example, making entries into a symbol table. So into a symbol table, you either install an ID or install a number that a Lex analyzer may be required to perform. Okay, Lex-like specifications can be even used if a Lex. Okay, so you also use this kind of specification if a Lex. Okay, we'll be talking about this code later. Okay, if So if Lex compiler is not available, okay, so even if your Lex compiler, so let me just complete it. Even if Lex compiler is not available, even then you can use those notations. Okay, the specifications can be manually transcribed, okay, into a working program. Okay, so you just need to know how you can write a regular expression and how you can associate those regular expressions to, you can write a dictionary kind of a thing, like this is a key and this is a value pair, right? In any programming language you can use that dictionary data type. Okay, and if dictionary data type is not available, you can customize, you can create your own kind of a dictionary value. You can merge multiple data types together to have this kind of a notation where you have multiple keys, you have multiple values, so that you can associate a key to a value. Okay, on this side you have a key, on this side you have a value. So that means I am saying that even if you are not having a Lex compiler, even then you can construct a program which looks like a Lex program. Okay, and later on those specifications, this kind of a specification can be manually transcribed into a working program using a transition diagram techniques. Okay, like I told you that the in this present session we are going to do what? We are going to translate a transition diagram into a code. Okay, and what kind of a code? This kind of a code. Okay, where on one side you have manifest definitions, on the other side you have a translation rules, and on the other side you have auxiliary procedure. Okay, so this kind of a language, this kind of a program that is consists of 3 sections, okay, is called a Lex program in fact. Okay, and if it is a Lex program, its extension will be L. Like C program has an extension C. Okay, C++ has CPP, text file has TXT, document has DOC, and similarly Lex program is going to have this extension L.L. Okay, so Lex is generally used in the manners depicted in figure 3.17. Let me just go through that figure. So this is that figure 3.17. Okay. Okay. This is okay. I just slowly move down, and then this is 3.16. This is 3.17. This is what it's talking about. Okay. So here we were, like, first, a specification of, let me just clear this whole stuff. First, a specification of a Lexical is prepared. First of all, you specify, you prepare this specification, okay, in the form of lex.l. Okay, so you write a code and you give a name to lex.l, for example, in the Lex language. Then you give it to a Lex compiler. Okay, a Lex compiler is going to convert it into a C code. So Lex compiler is a translator, okay, which convert a program written in L language into a program which is written in C language. So once you have a C program, okay, then you give it to a C compiler so that it can convert into an output file. Okay, and this output file is your LA, is your lexical analyzer. Okay, and later on, this a.out, you give a sequence of token to it, sequence of tokens to it, sequence of, sorry, not a token, but sequence of lexemes. Okay, or lexemes, or in short you can say you provide it a source code. Okay, and the output is sequence of tokens. Okay, sequence of tokens. This is so if you provide an input, a sequence of lexeme or a source code, and it is going to generate a sequence of tokens, which can be installed in a simple table, or it can directly also be given to the syntax analysis, which is the next phase. So this is what it is saying, that program, this lex.yy.c, so which is the output of a Lex compiler, consists of a tabular representation of transition diagram. So this is what? This is a tabular representation. So all the transition diagram, let's say this is the initial state. Okay, there are many states, and this is the final state. We have seen many transition diagrams in the last session. Okay, so this lex.yy.c, if you open it, you will see that this kind of a transition diagram. Okay, every transition diagram, for every transition diagram you have a tabular representation. If you have 5 transition diagrams, there are 5 tables. Okay, it's a tabular representation. This is a tabular representation of transition diagram constructed from the regular expressions. So transition diagram is constructed from RE. So initially you have RE, you translate that RE into what you call a transition diagram, and from transition diagram you need to know how to convert that into a tabular representation. Okay, so that tabular representation, once you are able to translate that into a tabular representation, then you can say that that is the output of a Lex compiler. Okay, and if you are able to do it manually, okay, so in that case you don't need a Lex compiler, because Lex compiler is used to do what? Lex compiler is used to do this thing. It converts a transition diagram into a tabular representation. Okay, so even if you do not know how to construct a transition diagram, you just provide a regular expression. Like here you provide RE, okay, regular expression based notation, because I told you that your lexical compiler, okay, this is lex compiler, which is one kind of a tool to generate a lexical analyzer, okay, is based on SPN, which is based on RE. Okay, so there are many tools which can be, okay, which can be generated out of it, and one of the tool is this lex compiler. Okay, so Lex compiler does this job. So this is what was meant when it was said, when it was mentioned that even if the Lex compiler is not used, even if the Lex compiler is not available, even then you can use the similar kind of notation. Okay, so you can do this kind of a job manually also. Okay, so lex.l, okay, consider from regular expression lex.l, okay, of lex.l together with standard routine that uses the table to recognize lexemes. Okay, so in an input it is full of lexemes, like here input it is full of lexemes, and output is sequence of tokens. Okay, so along with this tabular representation, okay, you also have some routines like subroutines. Okay, and this subroutine tells you how to identify lexemes. Okay, how to identify lexemes, and if a valid lexeme is found out, how to translate that lexeme into a token. Okay, so the action associated with the regular expressions in lex.l are pieces of C code, okay, and are carried over directly to lex.yv.c. Okay, so the actions which are written here in lex.l, okay, action are C code. So Lex compiler doesn't need to translate it into C code because it is actually a C code. It will be directly carried forward to it. Okay, but the other thing, okay, like tabular representation has to be translated. Okay, like it has to convert the transition diagram into this table, right? So the action that we talked about, that are already written in a C code. Okay, if you open L code, you will see auxiliary procedure, right? Auxiliary procedure. I told you that a Lex program has a 3 section. Okay, the first section is definition section. Okay, then you have a transition process. Okay, transition process, and then you have auxiliary procedure. So auxiliary procedure are the code written in C language. Okay, so when you transfer this to Lex compiler, it will just carry forward to on this side. Okay, it doesn't convert into C, it is already converted into C. Okay, so finally lex.yv.c is run through a C compiler to produce an object program a.out, which is the lexical analyzer. So this is what your lexical analyzer is. Okay, so this a.out is your lexical analyzer that transforms an input stream into sequence of tokens. Okay, I hope you're getting it.
Yes, sir.
Yes. And this is how the Lex program consists of. Lex program consists of declarations, and then
Yes.
you have translation rules. Okay, and then you have auxiliary procedures. And when I was talking about that, auxiliary procedures are the programs written in C language only. Okay, so Lex compiler doesn't do anything. It just passes it. Okay, it just passes it to the output program, which is lex.yv.c. So declaration section includes declaration of variables. Okay, so what do you mean by declaration? Declaration means declaration of variables, manifest constants, regular definitions. Okay, so what is manifest constant? You must have heard this manifest constant, okay, as a new term. So manifest constant is an ID, is an identifier that is declared to represent a constant. ID for a constant. Okay, for a constant. Okay, it's an identifier for a constant. So that is called manifest constant. Okay, and if you talk about the regular definition, see, variable is okay, you know what is a variable. Okay, variable uh, is like a container which contains something, right? It is a unit of a memory in which you can store something. So variable is okay. Manifest constant, I told you what is a manifest constant. It is an identifier which is declared to write to specify a constant, okay, to represent a constant. And regular definition, that means regular definition. So when we talk about declaration, it contains three things: one, variable, then manifest constants, okay, then you have regular definition. Okay, so if we talk about regular definitions, these are statements, okay, which are similar to those which we have already seen, okay, and are used as components of regular expressions appearing in the translation rules. Okay, so we'll see what an example, and then we'll be able to figure it out. What are these different kind of three things? So declaration sections contains three things, right? One is a variable, declaration of variable, then declaration of manifest constants, and regular definitions. Okay, so and then translation rule, like the second portion. Okay, like this is the first portion, this is the second portion, and this is the third portion, and all these three portions are separated by these two percentage symbols. Okay, and let's talk about, so we have already discussed about this thing, so this is thing is over. So let's talk about this thing. Okay, let's talk about this thing, translation rules. So what do you mean by translation rule? Translation rule is like once you figure out one particular pattern, then what is an action that is required to be done? Okay, let me just see here. Okay, this is how translation rule looks like. You have a pattern and then you have an action. Okay, uh, like you have P1, P2, P and so on up to Pn. Let's say you have n patterns. Okay, and then you have actions corresponding to them. Action 1, action 2, and so on up to action n. Okay, so PI is a regular expression, and each action AI is a program fragment that is written in C++ or C language, not C++, but C language, right? So this action, okay, this action thing, and this action thing which is mentioned over here, and the action thing which is mentioned in the third portion that I talked about, like your LEX program consists of three things. So this portion, auxiliary procedure, this also contains the definitions of functions which are referred to the action portion of a translation rule. So translation rule consists of pattern and action. So for this pattern, this is an action. Okay, for PI, action I. For P1, action 1. For P2, action 2. P1, P2, P3, whatever I'm talking about, these are patterns. Pattern 1, pattern 2, pattern 3, pattern 4, and so on. And for each pattern, there is an action associated with that. Okay. Okay. And yeah, so these are the actions. So this is how we write. Okay, so we write action in curly braces. Okay, and we do not write patterns in curly braces. Patterns are written as it is. Okay, each PI is a regular expression which is mentioned in the form of a pattern, and each action I is a program fragment that describes what action the lexical analyzer should take when pattern PI matches the lexeme. Okay, so see, the ultimate job of a lexical analyzer is to match a lexeme, okay, with a pattern. If a pattern says that this is that lexeme, okay, action says that, okay, now I'm going to generate a token. So what token is to be generated, whether to be generated or whether not to be generated? Suppose a lexeme of white space is encountered. Okay, there is no token associated for a white space, because that is one of the job of a lexical analyzer. It doesn't do anything when a white space is encountered. It does not create a token for a blank. It doesn't create a token for a tab or a new line. Okay, the third section, now we are going to talk about this third section. Okay, let's just so this section, auxiliary procedures. Okay, so we are done with definitions, we are done with translation rules. Now we are looking at this auxiliary procedure. That is the third section we have referred to. Okay, so let's talk about the third section. Okay, I think I have gone too far. Let me just go back slowly so that we can refer to that third section, which is auxiliary procedure. Okay. 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 Yeah. The third section. Okay, here the third section we are talking about, it holds whatever auxiliary procedures are needed by the actions. Okay, so in an action, in this action, sorry, uh, in this action or in this section or in any action, if you wrote a particular function to be used and that function needs a definition, you need to define it in the third section. It is similar like if you have written a C program or a C++ program. Okay, you have written a printf statement or a scanf statement. Okay, or let's say any other function which needs a definition. So we know that for printf and scanf, you have stdio.h file. So you have to include that file at the top. Without that, okay, you cannot use scanf or a printf method. Okay. So similarly here, what you do, you write the definition of those functions in the third section of the code. Okay. Third section holds whatever auxiliary procedures are needed by the actions. Alternatively, these procedures can be compiled separately and loaded with lexical analyzer. So this is another alternative. So in order to lighten the lexical analyzer, what you can do is you can separate the third portion, okay, and separately compile it, and later on you can load it along with the lexical analyzer. You can say that your lexical analyzer, okay, is based on only two kind of sections. One is the definition of definition section, other is a translation rule section. Okay, lexical analyzer created by Lex. So let's say we have created a lexical analyzer. Okay, that lexical analyzer, what is the lexical analyzer name? It was a.out. We have seen that a.out. That was an output of a C compiler. Okay, and that is the lexical analyzer which takes an input of us input which is full of lexemes and output it's going to generate which is full of tokens. So if that is the lexical analyzer we're talking about, created by Lex, behaves in concert with a parser. Okay, that means you have LA which is generated, like this is LA which is generated. It works in concert with a parser. Okay, what is parser? Parser is a syntax analyzer. So parser asks for a token and it gives a token to it. Okay, and it also at the same time it also saves token into symbol table. Okay, so symbol table is also kind of a repository which of a token, and parser can also get the token directly from the symbol table. Okay, when it says that Lex is created by Lex behaves in concert with a parser, that means it goes hand in hand as uh, in processing with the parser in the following manner. Okay, this is the manner when activated by the parser. Okay, so LA is activated by the parser. So parser activates LA. Okay, activates by the parser. Lex begins reading its remaining input. Okay, only on that when it's a active, okay, only then it starts reading its input. So input is in the buffer. Okay, so I told you that in a buffer it maintains two pointers, one is forward pointer, other is lexeme beginning pointer, right? So then it starts reading it. So these pointers are the pointers which are coming out of the lexical analyzer. Okay, so when activated by the parser, lexical analyzer is activated by the parser. Okay, the lexical analyzer begins reading its remaining input one character at a time until it has found the longest prefix of the input that is matched by one of the Lexical expressions pi. So it is going to, let us say printf is written, right? So p it will read, ri it will read, in it will read, t it will read, f it will read, and then it will recognize this. Okay, so these characters now it matches with the name of a function. Okay, so pattern, which is one of the pattern for printf, is the name of a function or an identifier. Okay, like printf can be an identifier. If it is an identifier, then it is identifier which is used as a name of a function. Okay, so as long as it will read character, one character at a time, p, r, then I, then n. Okay, let's say this is lexeme beginning will be pointing at here, forward pointer will keep on moving. Okay, forward pointer will keep on moving like this. Okay, and when forward pointer reaches this parenthesis, it will stop there. Okay, so whatever is in between lexeme beginning and forward pointer, not including forward pointer, is considered as a lexeme. Okay, and it is matched with the second portion, what pattern it is matching with. So one of the pattern for identifier matches with it. Okay, so then the corresponding action will be taken, okay, by the lexical analyzer. Lexical analyzer does that action in that case. Okay, I hope you understood what I mentioned, what I meant by when activated by a parser, lexical analyzer begins reading its remaining input one character at a time. I took an example of printf. Okay, so one character at a time of printf will be scanned, and it will keep on doing it until it is found the longest prefix of input that is matched by one of the regular expressions. So all these p's are nothing but regular expressions. And then it executes action I. Let's say pi has been matched with that pattern, and then action I will be executed. Typically, action I will return control to the parser. Okay, so after doing this action, it will return control to this parser. So it has this is the concerting way of working LA and parser together. Okay, parser activates LA. Okay, on getting activated by the parser, lexical analyzer starts reading its remaining input one character at a time, so long that that it matches a long enough lexeme. Okay, that can be matched by a particular pattern. Okay, and in against that pattern, suppose it is P2, in against that pattern, action 2 will be executed, and after that execution of an action, control is returned back to the parser. Okay, so parser is given control. However, if it does not, okay, then the lex analyzer proceeds to find more lexemes. Suppose it doesn't happen that after this action control is returned to the parser, okay, then lex analyzer continues with another lexeme. Let's say this is recognized as another lexeme, right? Until an action causes control to return to the parser. It will keep on doing so. Okay, it will keep on recognizing all the tokens. Okay, recognizing all the lexemes into the tokens as long as there is a return statement that gives a control back to the parser. So as long as lexical analyzer is in action, it will keep on scanning lexemes, converting into tokens, putting it into symbol table. Okay, and there will be an ultimate statement of a return statement, and that return statement will give control to the parser. Okay, this kind of discussion will help you in designing your own lexical analyzer, designing your own parser. Okay. 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 So the repeated search for lexemes. Okay, who is searching for lexemes? It's a lexical analyzer which is searching for lexemes. Repeated search for lexemes until an explicit return allows the lexical analyzer to process white space and comments conveniently. Okay. The lexical analyzer returns a single quantity that is called token. That is the token to the parser. Okay, it returns token to the parser. To pass an attribute value with the information about the lexeme, we can set a global variable called yyLval. So wherever in a code you see yyLval, okay, that is used to pass attribute of a token. Okay, so yyLval is attribute of a token. So LA returns to parser, that means syntax analyzer. Okay, and that thing is called token. Let me just say that this red dot is a token. Okay, and token also has an attribute associated with it. Okay, let's say this green thing is an attribute associated with it. Okay, and this green thing is called yyLval. Okay, so that yyLval is a global variable. Okay, so it is not going to be passed to a parser because it is a global variable. Parser will also have an access to that. Automatically it will have an access to that because it is a global variable. Okay, so that global variable yyLval is used to pass on the attribute value of a token. Okay, what do you mean by attribute value? Let's suppose ID is a token which is generated. Okay, and if it is ID for A, then A is an attribute. So we can set yyLval to specify that A. And suppose that A value is 5. Okay, so we can specify another yyLval to specify this 5 as a value. Okay. Okay. So we'll also see this occurrence of yyLval into the code, okay, of a LEX. So let's see figure 3.8 where LEX program is already written. Okay, that is a LEX program for recognizing tokens of figure 3.10. Okay, let's just go and look at this is the LEX program we were talking about. Okay, so this is the LEX program for tokens of tokens like relational operators, identifiers. Okay, like I told you that there are some of the like first portion, second portion, and third portion. Okay, and this is the first portion. This is the first portion. Okay, then you have double percentage symbols for the second portion, and the first portion I told you that in the first portion you have Three things. You have variables, you have definition of manifest constants, and you have regular definitions. And here in this particular case, okay, you do not have any variables here. Okay, you have definition of manifest constants and regular definitions. Okay, now definition of manifest constants, I told you what a manifest constant is. Manifest constant is an identifier for a constant. Okay, like LT is used as an identifier, LE is used as an identifier for a constant called less than symbol, for a constant called less than equal to symbol. And similarly EQ, NE, GT, GE, these all are the manifest constants for the relational operators. Okay, less than equal to, not equal to, greater than equal to. Okay, and these are manifest constants for representing the if then else, identifier, number, relop. Okay, and this is for regular definitions. Like I told you that the first section contains three things: variables, manifest constant, regular definition. And this is how regular definition looks like. Okay, like what do you mean by delim? Delim is delimiter. Okay, delimiter is a combination of a white space, tab, or a new line. Okay, like here is a space, you say that it is a combination of a space, so combination is specified using square bracket. Okay, and put some space, along with tab, along with n. Okay, you find any one of them, it is taken as a delimiter. So what is white space? WS stands for white space here. One or more occurrences of delimiter, like one space, two tabs, or two new lines, or one space, one tab, one space, okay, one new line. Okay, any combinations of these things, one or more, at least one has to be there. Okay, it's called WS. WS is white space. So that's the reason there is a plus outside this. Okay, so you have a curly brace, you write the definition that you have already defined, let's say delim. Okay, close the curly brace and write plus. So this is one or more occurrences of delimiter, and that is referred to as WS. Letter, how would you define a letter? Letter is from A to Z, capital, or from smaller a to smaller z, small. Okay, any combination of these things, or any one of, not combination but any one of this, like capital A is a letter, capital B is a letter, small a is a letter, small b is a letter. Okay, this minus sign is specifying a range over here. Okay, it is not saying that A has to be, Z has to be separated from A. It is not a subtraction symbol, it is a range symbol. Digit, what is a digit? Okay, digit is anything which is from 0 to 9. Okay, 0 to 9, 1 2 3 4 5 6 7 8. What is ID? ID is anything that starts with a letter, and after that letter there can be 0 or more occurrences of letters or digits. Like this is how you to specify. Okay, like 0 or more occurrences of letters or digits. So this says that, okay, whatever is mentioning over here, so you have star after that. Like plus is one or more occurrences, star is 0 or more occurrences. Okay, so this line is for or. This is a regular expression for ID. This is for digit. This is for letter. This is for white space. This is for delim. And this is for number. Okay. Number is anything like one or more occurrences of digits. Okay. And then you can have optional dot. Okay. And then you can have, after that dot, there has to be one or more occurrences of digits. Okay. And this question mark says that you have 0 or 1 occurrences. 0 or 1 occurrences of this thing. Okay, question mark means 0 or 1 occurrences. So these are some of the closure things which you need to understand, that this is called clean closure. Okay, which is used to specify 0 or more. Plus is used to specify 1 or more. Question mark is used to specify 0 or 1. 0 or 1. Yes, Nishant, you were saying something. You're not audible, Dishant. If you can write something in a text box, a chat box, so that we can answer. You're not audible at all. I hope I am audible, right? Okay, you can type your message. Okay, let me just continue. So this is for translation rules. Okay, and it says that what happens, what action needs to be done if you find a pattern. Like these are the patterns. All of these are patterns or regular expressions, and these are the actions. And some of the actions needs a definition. Okay, and those actions are these actions. Let's say install underscore id is an action, is a function which is user defined function. You have to define it. Install underscore num is also some function which you need to define, and where you will be defining, you will be defining at the third section. Okay, like here you can see, it is, they are defined here. Okay, like you have mentioned a skeleton architecture for defining them. Okay, at this moment it is only mentioned in a case of a comment that whatever you're going to write, it has to satisfy this thing. It is a procedure to install lexeme whose first character is pointed to by yy text and whose length is yy length, into a symbol table and return a pointer there too. Okay, and install underscore num, similar procedure to install a lexeme, that is a number. And we also talked about yyl. Yyl is a global variable which is used to specify the attribute of a token. Like if relop is a token, then attribute of that is lt. If relop is a token, and this is what you have found out, then you have, see, in all of these cases, whether it's less than, equal to, not equal to, greater than, equal to, all of them, for all of them, there is only one token which is going to be generated. That's called relop, because these are relational operators. But how are they different? They are different by their attributes. And for their attributes, you have yyl as a global variable, which is used to specify that these relational operators are of these natures. This relational operator that was found out was less than. Relational operator which is less than, equal to, yes, this is less than, equal to. Relational operator which is equal to, yes, this is equal to. Relational operator which is not equal to, yes, this is not equal to. This is how you specify not equal to. Okay, in one particular programming language for which there is a lexicalizer. And let's say if you are designing a lexicalizer for your language, and in your language it is like, for example, in your language it is like sign of exclamation and equal to. Okay, it's like in some programming language, this is what you call a not equal to, right? Sign of exclamation and then equal to. So in place of this, you just write this. Okay, so this any not equal to, this relational operator. Then you have a greater than. Okay, so yyl says that relop, which is of gt. So this for this it is ge stands for greater than, equal to. Okay, and relop. And then the third section is all about the definition of those functions. How are you going to install an id into a symbol table, or install a number into a symbol table? That will be specified in LEX program. Okay. Okay, this is it for today's session. I think we do not have much time. It's only 3 minutes left. Wait for attendance link. Okay, I'm stopping this whole thing. I'm stopping a share and stopping recording.